Today let us go beyond the understanding about the nature of light that was learned by the Arabs and by Newtonian optics. Let's go beyond Romer, Jupiter, and Bradley stellar aberration and Fizeau direct measurement of the speed of light measurement, as we did last time. You may ask, why light? That's because it's the tool we will be using from now on. It's how we learned about the heavens. By learning more, we may see how to build these instruments that will help us see further and better still. That's what happens next, historically anyways. And Newton contributed greatly in that field as well. I must point out, however, that right after Newton published math, physics, and astronomy in Principia, a lot of other fields of learning started to develop. Continuing development of astronomy and physics placed England as the strongest colonial power, in large part because of the advantages to its fleet. Chemical sciences helped France and then Germany. Microscopy, developed by Newton's nemesis Robert Hooke, started us on the road towards understanding living things, called biology. For much of our history, we were greatly influenced by the old Greek notion that light emerges from the soul and the eyes and illuminates the universe. This was not just a crazy idea. They actually used the fact that it was expected that an eclipse of the sun would cast a shadow on the permanent stars, and it didn't. Nobody knew how far those stars were exactly, but at the Greek time it was assumed that they were fairly nearby. Since there was no shadow, they assumed the light emerged from the eye. That picture changed in the Middle Ages with some experiments that we are not quite sure how they came about by the Arabs in the 10th and 11th century, and later on by Roger Bacon in England, and later on by Newton. But by the late 1700s, early 1800s, people were not happy with the description of light that Newton gave us. Thomas Young conducted a very neat experiment called the double slit experiment, where he got light from the sun to hit an opening in one wall, then two openings in the next wall, and see a pattern on an opposing screen that looked like maxima and minima. That actually proved that light, at least in some circumstances, behaves like a wave. Now guess what? If light behaves like a wave, what happens when it moves from a medium where it moves very, very fast to a medium where it moves a tad slower? Same thing as happens when a wave incident upon a sandbar is hitting that sandbar where it can only move a little slower. It changes direction. One way of imagining this is assume that the direction of the incident wave is like your 4x4 driving on a fairly good road. Then you go onto a sandy dune where it can't move as fast. It has to change direction when the right wheel enters the low speed zone. All those laws of nature are all about usefulness. Notice what happens when light rays, now behaving like waves, enter a glass. In a glass, light rays move slower. As a result, they change direction, then change direction again if the glass is flat. But if the glass is in the shape of a lentil, hence the word lens, then light coming from the right and light coming from the left focus at one focal point. Imagine that those lights coming from the right and the left actually arrive from an incredibly far away star. So we can merge all the light from that incredibly far star into a focal point and get enough light to get an image of a star. Now let's put two of those together, and what would happen is that the light from a star goes to a focal point that's the focal point of a secondary lens called the eyepiece. Then it goes into our own eye, resulting in magnification of the picture of whatever is going on very far away. Notice that the angle theta 1 on the very left side is small, whereas the angle theta 2 going into the eye is much larger. That would mean that the image forming on the retina in the eye is larger due to the fact that we have this device made of an objective lentil-shaped lens and a smaller eyepiece lentil-shaped lens. That's the principle of the telescope. A collector of a lot of light rays and a magnifier of objects. Galileo Galilei, the first person to actually check on the so-called Newton first and second law, was also a developer of the early telescope. The actual telescope was invented as somewhat of a toy in the Netherlands at about the same time that Galileo lived. He heard about it, developed it, and used it for both commercial purposes and for his astronomy. The following is a telescope that I have used about 12 years ago in a university called Bucknell University. This is made by one of the most famous telescope maker family in the United States, the Clark family. Therefore, this is a Clark refracting telescope that's still actually working and is used by hundreds of people every month in observing planets. It's one of the best ways of observing planets. Interestingly, not as good at observing things like galaxies. This is a similar telescope, it's slightly better shape, which is right next to Chicago. Now look at this refracting telescope. On the left you have a picture of it with one big lens on the left and small lens on the bottom right. The weight on the other side just makes sure that there is no torque on the telescope and it doesn't fall. On the right hand side, the lady is actually observing with the telescope, but at the very back there is a plate. This is called a photographic plate. In the mid-19th century, people started using photography, and right away some of them put a film at the back of the telescope, as you can see here. Of course, this picture is not from the 19th century, but the method is the same. As you are getting ready for this coming week, please try and answer the following questions. Try and see which of these is the correct answer.